Being one of the fastest developing nations in the world today, India needs to develop together and advance as a whole. It's in plain view that the more access we have to electricity, more is the scope for faster production and improved quality of life. Our villages, our strengths, the rural folk are still struggling to get access to electricity due to heavy load shedding and an infeasibility of grid supply in certain regions. This problem is what motivated Team IITB to create a device which can address these necessities of our age. The aim was to devise a tool that can power a typical rural household which can survive the rough rural environment and at the same time has the portability and modularity required to increase access among the villagers. Being a tropical country, solar energy is readily available across India and has great potential to be harnessed. As per the competition requirements, we designed the project within the specified budget of $1,000. The focus was on the reliability and ease of manufacturing to make fabrication possible locally.
It is basically divided into two major sub-teams. The first is the design and structures team. This team is tasked with designing, conceptualizing and fabrication of the device. The other team, the EPT or the electrical and power team, was tasked with sizing, designing the circuits for and testing the device.
The structure we have used aluminium as the base material, as the weight ratio is quite high, and again it is just good. The structure is made in two parts. Top part is for panels and smaller batteries. The bottom part is for bigger battery. Again, this structure is assembled with a 10 bolts for each of assembly, and these panels can be folded to compact mode with the help of hinges so that we can store and transport it easily.
For this battery segment, we considered several NIMH battery RSV capture, which can be easily removed for different applications as soon as they come out of the middle setting. Specifically for modularity, we consider that the panel structure and the battery section can be separated. So sometimes when the panel with a few of the batteries have to be transported, they can be easily unbolted. The dispatchability of the structure is that within 2 minutes, the panels and this segment can come out of the bottom segment.
So in order to size the PV system, first we have to consider the PV modules and the batteries. So out of the available technologies in PV system, we took the polycrystalline chrome solar cells, which are the most cost effective and weight effective.
We've taken 3 batteries into consideration, lead acid batteries, NIMH batteries and lithium-ion batteries. So in terms of weight, lithium-ion batteries are the most effective, whereas in terms of cost, lead acid batteries are the most cost effective. We have basically 3 major constraints. One is harvesting energy continuously for 3 days, the weight constraint and the cost constraint. So we have modeled this problem as a linear optimization problem in Excel. We modeled 3 cases. We found that using lead acid batteries and a mix of lead acid and NIMH batteries gives the same amount of power in 3 days, but we needed portable applications. We finally selected the third case, which is the mixture of lead acid batteries and NIMH batteries.
Amongst our batteries, we have a high voltage battery which can be used for community higher voltages and stack of small individual batteries which can be used for individual use. Major applications we have thought of is solar pump. Right now in Indian villages, people are using hand pump. When we power the pump with this device, we can make this work a lot more easier and will help to save the time of the Indian rural village.